Question 16. Now this question looks suspiciously familiar, and that's because it is. It's identical to question 22 from paper 1 of this exam series. So for completeness, I'm going to segue into my video of that question in here. Question 22A, part 1. A student investigates static electricity using a plastic ruler. Explain in terms of electrons why the plastic ruler is not normally charged. Well, our ruler looks like this. If we look close enough, we'll be able to see the atoms that it's made of. And our atoms, according to the Rutherford model, is some positive charge in the middle, balanced out by some negative charge. So let's say something along the lines of that. The plastic is made of atoms, and atoms have positive and negative charges. Those are the electrons, by the way. The reason that our ruler is not normally charged, it has no overall charge. The positive and negative charges are equal in amount and cancel to give a neutral ruler. So we've explained that our ruler does have negative charges, the electrons that was mentioned in the question, but we've demonstrated some physics here by saying, well, there's some positive charges there, and these positive and negative charges cancel each other out because there's the same amount of each, and that's why our ruler is neutral, or it's not normally charged. Question 22A, part 2. Explain in terms of electrons why the ruler becomes charged when the student rubs it with a cloth. In this case, electrons are transferred to or from the ruler when it is rubbed. For the time being, we have no idea whether we've removed electrons or provided more electrons because they haven't told us what the plastic is. But in either case, there will now be an unequal amount of positive and negative charges. Or you could say there is now a net charge, or they're not cancelling out. But 2 marks here for saying that where our electrons have been either moved from the ruler or to the ruler doesn't really matter, because the result is we now have either more positive charge or more negative charge on our ruler, which is why it becomes charged. Question 22b. The diagram shows the electric field between 2 charges A and B, B part I. State the charges of A and B. Use the diagram to explain your answer. Now, here we've got some field lines. Field lines show the direction of a force on a positive test charge. What this means is if we have a little positive charge here, it would, well, let's stick it on the line, there we go, let's make it really obvious. If we have a positive charge here, it would feel a force in this direction along the line. Let's stick another test charge here, see what happens. Here we go. This positive charge will feel a force in this direction along the line. That's what the field lines are all about. Knowing that, positive charges are repelled by other positive charges. So if our test charge here is moving away from B because it's following that field line, it's experienced a force in the direction of that field line, it must mean that B is a positive charge, because that's the same effect of having a positive charge here, a positive charge here, and there's a force effectively pushing them apart. So let's say that first. B is a positive charge as the field lines are coming out of it. With that in mind, our test charge, let's move it over here. It would feel a force towards A. That's a bit like having a negative charge and our positive charge here, attracting there. So by the same logic as before, A is a negative charge as the field lines are going into it. There we go. Seeing as I mentioned the effect on a test charge in my deduction of the answer, we might as well throw this in to ensure we get all 3 marks. I'm pretty sure we've got them there anyway, but let's just go for completion. The field lines show the direction of a force experienced by a positive test charge. Question 22b, part 2. Describe one similarity between the electric field line diagram and a magnetic field line diagram. There's a couple of things we can say here, but bear in mind they've put 1 in bold. So try to only say one thing that you're confident in, because if you put more than one fact and they contradict themselves, or you put one thing that's right and one thing that's wrong, you might end up shooting yourself in the foot and losing the mark. Pick the one similarity that you are confident is the correct one. Something we could say is field lines go from positive to negative, a bit like how field lines go from north to south in a magnet. So our similarity here, what we're trying to say is that the field lines are always going from something to something else. But another obvious similarity, which maybe we should have said in the first place, was field lines show the direction of force on a test charge for the for the electric field line diagram, or a test magnet in a magnetic field line diagram. Another good one is the density of field lines indicates strength of field. So field lines that look a bit like this is stronger than field lines that are, say, this far apart. If we have a look in this diagram up here, our field lines are pretty close together at this point, but then the distance between them is quite longer here, so our field strength is greater here than it is if we were in this region. So just one of these will do, and make sure you don't say something that contradicts the other. You shouldn't, because, well, you'll only be putting down the one thing that you're sure of. I recommend maybe using this one. This one's a good one to talk about. Or the field lines show the direction of a force on a test charge or a test magnet. That's also a good one to choose. Yeah. Question 22C. Calculate the charge when 200 joules of energy is transferred with a potential difference of 40 volts. Use this equation. Physics algorithm again. We've got some energy here. Potential difference 40 volts. Calculate the charge. So charge is Q. That's the thing we're looking for. Energy transferred. This one. Charge. Potential difference. You can substitute the numbers in, then rearrange, but I like to practice my algebra. Energy equals charge times potential difference implies charge equals energy divided by potential difference. Now put my numbers in. Energy is in joules, don't need to convert that, so 200 divided by 40 volts. Volts is standard, don't need to convert that. 200 divided by 40. Nice, that'll do. 5 coulombs of charge.